Trig sub can be tough. It really can. There's like a lot of little details in them, and a lot of the problems look the same, but then when you go solve them, they can play out really differently. I have 3 examples here today that I think basically have all the fundamental tricks in them, so hopefully this can help you get through some of these challenging problems. Basically what I'm looking for is how the number is combined with x squared. So if I have a number minus x squared, like in this first one, I would use sine. If I have a number plus x squared, then I'd use tangent. If I have x squared minus a number, I'm going to use secant, and that's just going to make it so that the trig identities are going to somehow condense and turn my expression into one thing. So anyways, in this problem, I see x squared minus 4. So I think I'm going to use for this one, x is equal to 2 secant theta, and then dx will be 2 secant theta tan theta d theta. And let me plug all these things in, and hopefully I'll be able to use a trig identity to reduce that expression underneath the square root. So what happened here is I just plugged everything in. The reason that I chose this 2 right here in front of that secant is because then once I plug it in for x squared, I'm going to end up with the same thing right there. Both of those are 4. Then I can factor that 4 out like this, and I'll be left with secant squared minus 1. And then I can turn that into tangent squared. So basically what that's going to do is take everything underneath the integral and turn it all into a single object so I can cancel out these square roots. So let me do that. Also, there's going to be some other canceling. I think you can see here these secants are going to cancel and those 2's are going to cancel. So let me simplify this whole thing down. Okay, this is kind of fun. This whole expression right here got simplified all down to a tangent. And then this squared right there is going to cancel with that square root, and this 4 is going to get square rooted and turned into a 2. So then I end up with just a single copy of tangent here and a single copy of tangent there, so then I end up with tangent squared. All right, so we've done the trig sub part of this, and now what's left for us to do is to just solve this trig integral. This is just the standard trick for how you integrate tangent squared. So I'm going to bring that 2 out front, and then I'm going to use a trig identity here. Tangent squared is secant squared theta minus 1, and then d theta. And now this is pretty easy to do the antiderivative of. What did I take the derivative of to get secant squared tangent? And then what did you take the derivative of with respect to theta to get 1 just theta? Okay, so brilliant. We've worked this whole thing out. The only issue is our answer has a whole bunch of thetas in it, and the original problem has a bunch of x's in it. So now we need to come up with some way to turn our thetas and tangent of thetas back into x's. So just a little bit of right triangle trigonometry. Let me get that set up so you can see how that plays out. The way that you turn your thetas back into x's is you just reference back to that original substitution that you made. So I'm just going to do a little algebra here to get the thetas by themselves, basically. So the things that I'm trying to figure out is what can I substitute back in for tangent of theta and just theta. So if I isolate the secant right here, then what I can do from this is just take an inverse secant on both sides. So from this equation, what I get is the inverse secant of x over 2 is equal to theta. So now I know what to do with just this theta, but I'm not sure what to do with this tangent. So let me use some SOHCAHTOA here. So secant is 1 over cosine. So then I just reciprocaled both sides, and I get 2 over x is equal to cosine theta, and the cosine is equal to the adjacent over the hypotenuse. So the adjacent over the hypotenuse And then that leaves the opposite side right here must be x squared minus 4, because that way a squared plus b squared equals c squared. All right, so now I'm trying to figure out what to plug back in for tangent. So tangent is opposite over adjacent. So here I have opposite over adjacent minus theta. That's it. That's it. So basically the way that these play out is you look at the expression that you have in your original problem, and based on that, you're going to decide which trig sub to make. Then you just do a whole bunch of plugging in, and there should be some basic trig identity that lets you turn those two pieces down into one piece so that you can cancel out some square root or whatever the issue is in the problem. And then that's going to leave you with just like a basic trig integral, which you're going to have to work out. And then when that is all done, then at the end of it, there is a little right triangle trigonometry problem to turn everything back into x's. All right. That was fun. I enjoyed that. Let's do a few more. I'm going to calculate this integral. It's a definite integral. It has a bit of a funny upper limit of integration there, 5 square root of 3 over 2, but you know, whatever. So I see an expression of the form 25 minus x squared. So that makes me think that I want to use x equals 5 sine theta, because then I'm imagining when I plug that into this, I'll get something that's like 25 minus 25 sine squared, and maybe I can turn that into a cosine or something. So then I get dx equals 5 cos theta, d theta. Okay, and now I'm ready to start making substitutions and evaluating the integral, but I have to worry about these limits of integration here really fast. So let me just work out what those thetas are. I'm trying to figure out the new limits of integration after you make a substitution. So I'm just plugging the x values right here into this equation. And that's giving me this, the sine of theta is equal to the square root of 3 over 2. So what you can do, I got pi over 3 from my little unit circle picture there, but if you want to, you can also just like do a sine inverse on both sides. The square root of 3 over 2. And you're going to get 60 degrees, so pi over 3. And then likewise, you know, what the sine of what angle gives you 0 is 0. All right, let me plug this stuff in and start working out the antiderivative. Okay, so what I did here is I just started plugging everything in for all the x's and for all the dx's. So, you know, just to be clear, when you put 5 sine theta into x squared, you get like 25 sine squared theta. And now I think that this thing on the bottom, I'm going to factor that 25 out and then use the basic trig identity to get some cosines, see how this goes. Okay, this is kind of fun here. So what happened next was I got this and I factored out the 25 and then I had 1 minus sine squared theta. So then I plugged that in right there. 1 minus sine squared theta, I made a cosine squared theta. And then, so now I'm just doing this to the 3/2 power business here. So this, when I put this 3/2 power there into the cosine squared, I have like cosine squared times 3 over 2. So that's how I just got a cosine cubed. And then I was just being a bit lazy. I didn't want to think about what happened with all these factors of 25. So I got my little calculator here. It's kind of fantastic. When I did it, they all canceled. I have a 25 here in the numerator, and then a square root of 25 cubed in the denominator. Oh, so I guess that's 5 cubed. Oh, so I have 3 factors of 5 in the numerator and 3 factors of 5 in the denominator, so they all canceled. And now I have this expression right here. So one of these cosines is going to cancel with that. So then I'm going to have a tangent squared. Oh, let me write these notes. I think I see how this is going to play out now. So what I did is I used this trig identity to trade tangent squared out for 1 minus secant squared. And then the reason is because this is going to be easy to do the antiderivative of. The antiderivative of 1 with respect to theta will just be theta, and then the antiderivative of secant squared is just going to give me tangent. So that's it. Now I just need to plug in these endpoints and work out the final answer. Okay, so it all just sort of fell out nicely. After I turned it into 1 minus secant squared, then I got these antiderivatives. So all that was left for me to do was plug in these two endpoints so we can work out the numerical answer. Now I got to work out this tangent of pi over 3, but luckily I already got my little reference triangle there. So the tangent of pi over 3 is going to be the sine over the cosine. So what I'm doing here is the square root of 3 over 2 divided by 1/2. So those 2's are going to cancel right here. So then also the sine of 0, what angle could give me a sine of 0? 0 divided by 1, so I'm getting 0 there. So this final answer here is just going to be pi over 3 minus the square root of 3. All right, so that was kind of a fun problem. Let me just clean up these notes. Okay, so there it is. If you're taking notes and you want to pause the video, here's my final worked out solution. Okay, so this time I'm going to do 9x squared plus 1 is the expression that I see inside my integral. So I have a combination of x squareds and numbers that has a plus in the middle. So I'm going to choose this time x is equal to 1 over 3 tan theta. And the goal is then when I plug that in for that x squared right there, hopefully the 9 will cancel out. All right, so then dx is going to be 1 over 3 secant squared theta d theta. All right, let me plug this stuff in and see where we get. And then I plugged all that in on the inside there. So tangent squared plus 1 turned into secant squared. Oh, but it's squared. So this needs to be squared right there. So a lot of these things are going to simplify. This 1/3 is going to simplify with that 6. And then I think I'm going to have a bunch of secants left over that hopefully are going to simplify as well. Let's see how that goes. Yay, it's happening. So I end up with this secant squared right there. So that's that secant squared right there. And then I have a secant to the 4th that ended up down there. And so 2 of them canceled. So I end up with 1 over secant squared. And so secant is the reciprocal of cosine. So I end up with cosine squared. All right. And then now we find ourselves in this familiar situation, which is you do your trig sub, and then you end up with basically like a standard trig integral. And this cosine squared is a standard trig integral. What you need to do is this like half angle formula. So I'm going to make this 1 plus cos 2 theta all over 2 d theta. And then that's brilliant because this 2 right there is going to cancel with that 2 right there. And so I am ready to do some antiderivatives. So an antiderivative for 1 with respect to theta is theta plus 1/2 sine 2 theta plus c. And let's just check. I'm doing that in my head, and the way that I do this is the guess and check method. So let's check and see that when I take the derivative of this, I do really get that right there. Okay, so first of all, the derivative of sine is cosine. And then when you take this derivative, you're going to have to do this chain rule. So I'm going to have to take the multiply by the derivative of 2 theta, and that's going to give me 2. And that's going to cancel with that 1/2 right there. So I am, in fact, just going to get cosine 2 theta. Okay, so brilliant. We did this antiderivative. We've done that part. And now all we have to do is turn everything back into x's. That's a bit of a unique challenge this time because this is the sine of 2 theta, and all of our original substitutions have just x in terms of theta. All right, so we are going to need one more trig identity in order to solve this problem. So the sine of 2 theta is equal to 2 sine theta cosine theta. So that's the way that we deal with this issue. It's common that you end up with a 2 theta on the inside. And so then when I plug that in, the sine of 2 theta is going to become 2 sine theta cosine theta. And that's exactly what we need it to do, because all of our original substitutions have thetas in them. They don't have 2 thetas in them. So that's what happened here. This sine of 2 theta turned into expressions that just had a theta in them. And then it's also kind of beautiful. This happens a lot. That 1/2 is going to cancel with that 2 right there. All right, now I need to do the little right triangle trigonometry part, and then we're going to be done with this problem. So I look here, and I solved for tangent, and I got tangent, it is equal to 3x, really 3x over 1, and the tangent is the opposite over the adjacent. So in this picture, I put my little theta down there in the quarter, and opposite over adjacent, and then Pythagorean theorem gave me that expression there. All right, so that's it. We're ready to write out the final answer here. So this is going to be the inverse tangent of 3x plus, and then the 1/2 and the 2 cancel. So now I just need to do the sine of theta. So sine is going to be opposite over hypotenuse, and then times the cosine of theta is going to be adjacent over hypotenuse. This was a lot of work. If you made it till the end of the video, way to be. Trig sub is a complicated process. If I did something wrong, or if you have any questions about how this went, please let me know, and I'll see if I can help you. So thanks for following along. Have a good day.